We propose a new simple network architecture, the transformer, based solely on attention mechanisms, which outperforms existing models on two machine translation tasks and English constituency parsing, training faster and requiring fewer resources. This paper introduces the transformer, a new model architecture for sequence modeling and transduction tasks like language modeling and machine translation. It uses an attention mechanism instead of a recurrent network to draw global dependencies between input and output. This allows for more parallelization and has resulted in better translation quality with much less training time than before. The transformer is a transduction model that relies entirely on self-attention to compute representations of its input and output without using sequence-aligned RNNs or convolution. Self-attention has been used in many tasks, such as reading comprehension, abstractive summarization, textual entailment, and learning task-independent sentence representations. Most competitive neural sequence transduction models use an encoder-decoder structure with a stacked self-attention and point-wise, fully connected layers for both the encoder and decoder, shown in Figure 1. The encoder is composed of a stack of 6 identical layers, each of which has 2 sublayers, a multi-head self-attention mechanism, and a simple, position-wise fully connected feed-forward network. The decoder is also composed of a stack of 6 identical layers, with an additional third sublayer which performs multi-head attention over the output of the encoder stack. Both the encoder and decoder employ residual connections and layer normalization to facilitate their outputs. Attention functions map a query and a set of key-value pairs to an output vector, where the output is computed as a weighted sum of the values based on a compatibility function between the query and the keys. Scaled dot product attention is an attention function that maps a query and a set of key-value pairs to an output vector. The output is computed as a weighted sum of the values, where the weight assigned to each value is computed by a compatibility function of the query with the corresponding key. It is similar to additive attention and dot product attention, except for the scaling factor of 1 square root Denmark. Additive attention computes the compatibility function using a feed-forward network with a single hidden layer, while dot product attention is faster and more space-efficient in practice. Multi-head attention is an attention mechanism that uses multiple attention functions with different linear projections of the queries, keys, and values to allow the model to jointly attend to information from different representation subspaces at different positions. The transformer uses multi-head attention in 3 different ways: encoder-decoder attention, self-attention in the encoder, and self-attention in the decoder. We add positional encodings to the input embeddings in our model to make use of the order of the sequence. We use sine and cosine functions of different frequencies for the positional encodings. Self-attention layers are faster than recurrent layers when the sequence length is smaller than the representation dimensionality and require fewer sequential operations, while having a maximum path length between any 2 input and output positions. They can also be more interpretable, as individual attention heads can be shown to exhibit behavior related to the syntactic and semantic structure of the sentences. We trained our models on the WMT 2014 English-German and English-French datasets using byte pair encoding, with a batch size of 25,000 source and 25,000 target tokens. We used 8 NVIDIA P100 GPUs, with 0.4 and 1 second step times for the base and big models, respectively. We trained for 100,000 and 300,000 steps, respectively, and used the Atom Optimizer. Our transformer, big, model on the WMT 2014 English to German task achieved a new state-of-the-art BLEU score of 28.4, surpassing all previously published models and ensembles. For English to French, our big model achieved a BLEU score of 41.0. We compared our results to other model architectures from the literature and found our models to have better translation quality and lower training costs. We presented the transformer, an attention-based sequence transduction model, and showed that it outperforms recurrent and convolutional architectures on translation tasks. We plan to extend the transformer to other tasks, such as image, audio, and video generation, and to investigate local, restricted attention mechanisms.